Hey everyone, welcome back to my channel. In this video, I'm gonna go over part 2 of tensors tutorial for PyTorch, beginner tutorial. This is the part 2 of the tensors. So we are gonna focus on matrix multiplications. So first, we need to connect to the GPU, and then here's the command that we can check using NVIDIA SMI. Just gonna zoom in. So we're using a Tesla T4 GPU with the CUDA version of 12.2. I think last time covered a matrix multiplication only using a matmul. So today I'm gonna compare Torch today I'm gonna compare .mm versus torch.matmul. So they both perform matrix multiplication in PyTorch. There are some major key differences to consider, when you use them. So number one is the broadcast stability, broadcast ability. So this is the number one thing. Torch.mm performs without broadcasting, and it requires both matrices, both inputs. Let's say both inputs to have exactly the same dimensions. So if the dimensions are not the same, they'll raise an error. You'll get an error. So for torch.matrix multiplication, matmul supports broadcasting. See, basically this means if one input has a fewer dimensions than the other, it will automatically expand it to match the dimensions of the other input. So it is very useful for tasks like multiplying a vector by matrix. So we'll dive into this later. And number 2 is performance. So torch.mn generally, I say this as generally faster for cases where broadcasting is not needed and both inputs have the same dimensions, and this is because it uses specialized routines optimized for matrix multiplication. It uses specialized routines optimized for matrix multiplications. Matmul, the other hand, is slightly slower due to the overhead of handling broadcasting, but it offers more flexibility and eliminates the need to check for matching the dimensions. And the third one is the use cases. So torch.mm is the common scenario, is a common use case. Basically multiplying two weight matrices in a neural network layer, and torch.matrix multiplication, it's like when you need broadcasting or you want more flexibility with your dimensions for your inputs. And this is very useful for tasks like multiplying a vector by a matrix, or multiplying a batch of matrices with different shapes. We covered about shapes in the previous video. So think of it like this. So Torch is a very strict and rigid, and you have to do exactly as it's instructed. Both inputs must match, and Torch MetMul is like a helpful, very flexible, so it will help you even if the dimensions are not lining up perfectly. So what do you mean by that? So we're gonna do some examples. So let's start with simple example. If you remember this function, I covered this in the previous video. So basically 5 by 3 1, 2, 3, 4, 5 rows, 3 columns. Okay, and then we're gonna do 3 by 2. Okay, they should work for both Torch and Torch MetMul because the same dimensions. Because 5 rows, 3 columns, and 3 rows, 2 columns. So 3 is matches. So it should work. Okay, let's do it. Let's do both operations. .mm. Okay, let's do B. So C2. And we're gonna print shapes. We should get the same shapes for both operations. So we get the same shape. So let's try a case where dimensions don't match. Let's try this. Two, 4. So now we're gonna multiply with the A, matrix A, and it shouldn't work because of 5, 3 versus 2, 4. So we're gonna try and catch the error. A, C. Except runtime error SE, and we're gonna print the error message. I'm gonna use the F string. So now shapes cannot be multiplied because 5 by 3 versus 2 by 4. Okay, let's do so now let's do an example about broadcasting. So let's do broadcasting example. Let's do this. So so we're gonna versus 5, 3. So that's, so if you remember, torch.matmul automatically broadcast a vector to match with matrix dimensions. So C1, gonna use matmul, and we're gonna print the shape of the result. C1 shape. So 3 matches with the V. And let's see. Okay, let's try torch mm. So we know it's gonna throw an error, so let's try torch.mm and catch the with the except runtime error sc print f string must be a matrix. So this is the error. Okay, let's try. So we did the mm and then let's do some examples about tensor device. So here's how to check the tensor device. Let's say if your tensor is GPU or CPU, this is, and if you want to use, so default is a CPU. So I'm going to show you how to change to GPU, how to move your tensor to GPU. So let's print tensor device. We should get a CPU because it's the default is a CPU, even though on the T4 GPU it's by design. So if CUDA is available, GPU tensor.2 to CUDA print f string GPU tensor print tensor device to check GPU tensor.device. If it's not available, print GPU is not available. So now, first it's on a CPU, then we move the tensor to a GPU tensor. Not necessary. GPU tensor and the CUDA device to the CUDA 0. Okay, what else? The GPU tensor also print out the device CUDA. But if you just want to see the device, you don't really have to print the tensor.device. Okay, let's try another example with the tensor device. This time, let's try and benchmark the speed. So let's see. Okay, we're gonna need to input time to time it. And then let's try different matrices. Let's start with the matrix dimension dimension. So 10 dimension, we're gonna create the random 10 by 10. Same thing. Ten by 10, and we can print a dot device. B dot device. Let's see, CPU. Let's try start matrix multiplication time. Let's try and time it. Torch.mm. I'm gonna focus on the mm and matrix multiplication. So n mm, I guess, equal to time. Okay. In mm minus start this should print out the, should get the mm time, so matrix multiplication time. Let's see, how long does it take? 0.00017 seconds. So how about 100 dimensions? 0.006. How about 1000 dimensions? 0.29. Okay, so let's compare this with the matrix multiplications, I guess. So start, we're gonna use the matrix multiplication to compare with the .mm versus .matmul. So I'm gonna do the same thing, time. Gonna do the operations, matrix multiplication, comma b, and matmul equal to time. Same thing here, just matmul time is equal to n and the difference. So the difference is 0.004. So time is faster. How about if we give too large of a dimensions? I think Google Colab is gonna complain. Let's try 2000. 0.005. Let's try 4000 dimension. Oh, matmul start to outperform .mm at 4000. Okay, let's try 5000. It's underperform again, so it's hard to tell once the dimensions get higher. How about 6000? Remember, they both have the same dimension, so matmul is kind of optimized. See, so it's still 6000, still outperform. That was the rare case at 4000. Let's try this again. It's usually outperform. Okay, how about 10,000? think it's gonna throw an error. It's too large for Colab to handle. Maybe we'll see. Of course, it's gonna take for a while. This is a really huge matrix. It's 10,000 dimensions. Okay, still faster. Okay, let's try this on CUDA on a GPU instead of CPU. So we're gonna use the same. Let's start with 100. If remember, we use the torch.CUDA is available. Then we're gonna torch.run and device. Now we say CUDA, otherwise it's gonna be on a CPU. We wanna do the same operation on CUDA this time on the GPU. So same thing. Just gonna copy it. Okay. Now we're gonna print the device. Same thing instead of. Okay. Else print CUDA is not available. So let's see. Okay, now we are on CUDA before we. So we're gonna do the same thing, but this time on CUDA. Same thing. We're gonna start the timers. Time. Okay, now we have the. I want to check the difference between time. It should be the same as the minus menu. Okay, let's see. Okay, let's compare the two. Oh, need to print out. Print the difference. Okay, performs faster than. How about dimension 1000? Same thing. So on CUDA. What about 10,000? Hopefully it won't throw an error. Oh, 1,000. How about 20,000? Yep. performs better. Faster than. How about 50,000? Okay, out of memory. Okay, how about 40,000? Let's see. Yeah, cannot do 40,000. How about 30,000? No, cannot do 30,000. So just 20,000, I guess. Alright, so these are the two examples of using GPU versus CPU. Oh, and also we can synchronize the CUDA. Let's see. Let's see how it performs. Yeah, same. Okay, so the performance gap between generally like widens if we have really huge dimensions. But this mainly like also depends on the specialized hardwares like GPUs for efficient computations. Okay, so let's cover. What should I cover? Okay, let's revisit data types. So the default data type is default D type. Torch float 32 and float tensor. Ah. 2.0.0. And so if we want to change to a different data type, we can do this by, let's say, gonna change it to double. If we want to use different data type instead of default. So our same thing, we're just gonna copy this. And then what we need to do is define the D type. Go to torch.float 64 instead of 32. Tensor.dtype. So this is how you define the data type when you define the tensor. Okay, and we can do booleans. Data type tensor torch. I didn't cover this in the last video. I don't remember. I think I missed these data types. So false, let's say true. So this is the Boolean data type. Torch.bool. Then we can print D-type. It's a Boolean data type. And what else? And we have integer, float 16, complex. You can play with those. And I want to cover some shaping and reshaping. The shape of a tensor, you can do this. Let's say tensor torch.tensor. Let's say 1, 2, 3, 4, 5, 6. Shape 2 by 3. Okay, And let's reshape this to shaped matrix. Matrix dot view to 2 by 3 to, let's make it 3 by 2. Okay, need to define the matrix. Oh, just use the tensor. Okay, let's shaped. So we started out with 2 by 3 and now we should get 3 by 2. So how to reshape the view. So, and we can see also shaped matrix. So 1, 2, 3. So here, here we have 2 by 3 by 2 by 3 to 3 by 2. Okay, so basically this allows you to reshape specifying the desired new dimensions without changing the underlying data. So the data is the same, we just reshape the matrix. Okay, and we can also use the automatic inference of dimensions. So what we can do is let's use a different name, but just to make it simple, let's say original tensor is a reshaped tensor so original tensor dot view -1 and 2. This is called reshaping with automatic inference. Okay, so we're gonna print both original and reshaped. Original tensor reshaped tensor. Just gonna print it out. So this is reshaping with automatic inference. This is and how about another example? Okay, this time we'll do original tensor, but one row. So this is the original tensor, let's say. And same thing, we can print the original tensor shape. So here's the original tensor and original tensor shape. Okay, now we're gonna do the same thing to reshape. Okay, let's see. So this is the variable length squeeze sequence of numbers. Okay, let's do squeezing and unsqueezing and call it. So for this video, I guess, hopefully I cover all the basic tensor stuff in these two videos. If not, please let me know. So let's do the squeeze and unsqueeze. Squeeze tensor. So I'm gonna squeeze the original tensor. Squeeze, and then let's try unsqueeze. Then original tensor, unsqueeze. Original tensor, squeezed and unsqueezed. What's going on with okay, let's see. Do you see the difference? So here, unsqueeze and squeeze. Okay, I guess just gonna call it for this video. If you have any questions or comments, please let me know.